Alright, 6.5, Advanced Interpretation of Exponential Models. Objective, students will be able to rewrite an exponential function in order to analyze its rate of change even with a different unit of time. Okay, first example one here. Ocean sunfishes are known for rapidly gaining a lot of weight on a diet based on jellyfish. The relationship between the elapsed time, there should be a T there, I apologize, in days, since an ocean fish is born, and its mass, m of t in milligrams, is modeled by the function m of t equals 1.35 to the t over 6 plus 5 power. Complete the following sentence about the daily percentage change in the mass of the sunfish. Every day there is a blank addition to or removal from the mass of the sunfish. Now, here they want us to circle one of these two. Now, we already know that it's gaining a lot of weight. So there's obviously an addition to and not a removal from. But what is that percentage per day? Now, your instinct might be, oh, there's a 0.35 there, 1 plus 0.35, that's a 35% increase. But it's not, because it's not every day, because the exponent isn't just t for days. Notice the exponent is t divided by 6 plus 5. So what we have here is we have our function is in a very funky format. And we want it to just have a t in the exponent. That way, whatever is in our parentheses will give us exactly the change in days. So one of the first things I see that we could do to kind of change our function here is when I'm adding exponents, like I am here, that's the same thing as multiplying something with the same base, but different exponents. So this is the same thing as 1.35 to the t over 6 times 1.35 to the 5. And so I can actually calculate what this number would be, 1.35 to the 5th power. I put that in my calculator and I get about 4.48. So this is really like saying 4.48 times, and isn't t to the 6 kind of like saying 1.35 to the 1/6 times t? That's a 1 over 6 there if you can't tell. So 4.48 times 1.35 to the 1/6 times t, right? Because that's exactly what t over 6 is. It's 1/6 times t. Well, if I'm multiplying these exponents, that means that I could actually write it like this. I could write this whole function as 4.48, 1.35 to the 1/6 power to the t. And now I have the exact same function, but now I've used my properties of exponents to rewrite it in the basic exponential form, where I have the principal amount, I have some rate, which I have yet to simplify, and then this is t in days. So now whatever this rate is in here will give me t in days. Will be based on a change per each day. So let's go ahead and figure out what is 1.35 to the 1/6 power. Well, it looks like it's 1.05 when I plug it in my calculator. So this is like saying 4.48 times 1.05. I'm rounding here to just 2 decimals to the power of t. So again, all I did is do 1.35 to the 1/6 to simplify this. So this is actually the function as I want to look at it, which changes things dramatically now when we're talking about just based on each day. Before, this actually wasn't each day. This was, if I was to plug in 1, it'd be 1/6 plus 5. So if I plugged in one day, I'd actually have a 5 and 1/6 exponent, which doesn't really make sense for the rate of change. So now I can see that it's actually a 5% change each day, because now when I plug in a 1 into the t, it's going to just give me it's just going to give me 1. Before, in order to get a 1, I'd have to, I don't even know, what could I plug in? Maybe a negative 24 or something like that. So it'd be really funky. So now I can actually get a 1, plug in one day, and get the change in just one day. So there is a 5% addition to the mass of the sunfish. Okay, that's it for example 1. Example 2 is very similar. So I want you to go ahead and give it a try on your own. It is an example question, not necessarily a practice question. So I just want you to give it a shot and see if you could figure it out. If not, no big deal. I'm going to work it out for you guys in just a second. But give it a try first. Okay, hopefully you give it a whirl. Let's read through the problem together here. The amount of carbon dioxide, CO2, in the atmosphere increases rapidly as we continue to rely on fossil fuels. The relationship between the elapsed time t in decades, that was important, hopefully you saw that, in decades, since CO2 levels were first measured, and the total amount of CO2 in the atmosphere, which is going to be represented by a decade t to denote that we're talking about decades, in parts per million is modeled by the following function. A of t, or a decade of t, equals 315 times 1.06 t. Complete the following sentence about the yearly rate of change in the amount of CO2 in the atmosphere. Every year, the amount of CO2 in the atmosphere increases by a factor of blank. Now, whenever they say factor of, it's going to be whatever's inside these parentheses. However, here they're talking about every year, and this function talks about every decade. So we got to do a little bit of thinking here. Remember, if t represents a decade, then that makes us have to stop and think about what exactly is the relationship between t and years. And let's say that y equals years for now, so that we can have a different way of thinking about this. So I need, right now my function is dealing with decades, and I would actually rather it deal with years. So let's think about, well 1 year, isn't 1 year 1/10 of a decade? Or you could think of it that if you were to take t, and if that represented 1 decade, you would multiply it by 10 to give you the number of years, right? So for example, if you had 1 decade, 1 for t, 1 times 10 is 10 years. And so you have a little equation here that relates decades to years, correct? And so let's say you wanted to get t all by itself, right? Because t is all by itself in this equation. Well, we could divide by 10 and divide by 10. And so we get that t equals y over 10. And this should make sense, because if I plug in 1 here for y, for 1 year, well, that should be 1/10 of a decade. And so that's what we would have here. Or 5 years, that would be 5 over 10, which reduces to 1/2 of a decade, which is what we would have for t. So now we have this other unit of time that we're going to plug into this function. And so instead of making it based on t for decades, we're going to make it based on y for years. And that's totally fine. We're allowed to do that. So let's just change it up here. So now we could say that a, and let's call it a of y, because it's a in years now, equals 315 times 1.06. But instead of t now, remember that t is equal to y over 10, so we're going to put y over 10 here. Okay, now that we've done that, we're going to need to manipulate this just a little bit, because remember, we don't want y over 10 over here. We want just y up there, because if we have just a y up there, then the number inside these parentheses would tell us the percent change, or the factor that it's increasing by every year. Right now, it's still telling us every decade, so we want to know it every year. So let's play with this. Remember, now this is the same thing as saying 315 times 1.06. And instead of saying y over 10, couldn't we say 1/10 times y? And this is where it gets really interesting, because remember, we have this 1/10 here. It's multiplied by y, which means that we could move it inside as an exponent here. And now our equation has just a y out here as the exponent. We just need to figure out what this is. So we're going to use the calculator to do that. 1.06 to the power of 1/10 gives me 1.006. I'm going to round there for now to the y power. So it's actually a really tiny amount of change percentage-wise, because it's less than 1%, right? It's about 0.6% or 0.006 change. So now we have it in a format that is telling us information per each year. And so every year the amount of CO2 in the atmosphere is increased by a factor of, well, this whole number here is the factor. So we should be able to just say 1.006. And if they asked around to decimals, which they might, we would just round this to say it's a factor of 1.01. That does round to 1.01. So that's what we would write right there. It's a little bit small for me, so I'm just boxing it right here. So that's all there is to this problem. It's, again, just taking our function and manipulating it so that it's able to give us information about what exactly we're asking about. See, this one's asking about every year, but the problem itself was asking about every decade. All right, see you guys on the next video.